Hi everyone, we're going to go ahead and get started on section 1.3, functions and their representations. And there are 8 different items that we want to cover today. And we're going to talk about interval notation and function notation and just how to write functions as sets. And we're going to just jump into it, and then we'll meet each of these objectives and we'll move to section 6.4. So the first thing we want to do is learn about interval notation. The following number line graphs describe different intervals. So an interval is a set of data, particularly in these graphs on a number line, where we're including a particular piece of that number line in our set. And so there are different endpoints. Sometimes they're marked with parentheses and sometimes they're marked with brackets. So these are parentheses in the first one, whereas the brackets are the red pieces that look more like plugs into a wall. And so the difference here is that when you have a parentheses, that means we're going up unto that number, but not including that number. So parentheses, not including, they do not include endpoints. Okay. And you can notice here that we have um, less than or greater than symbols, less than or equal to, greater than or equal to. We'll introduce some of those later, but if it's strictly less than or greater than, then that means we're not going to be including those endpoints. However, if they have the or equal to piece, then we will be including it. So you'll use hard brackets when you have or equal to, and you'll use soft parentheses when you have strictly less than or strictly greater than. Okay. So it says note, this is an open interval. An open interval are these parentheses right here. Okay. Both of those are open, so meaning we'll go up into those points, but we're not going to include the -2 here or the +2 here. And then this next one is a half open interval where we're not including the -1, but however, we are including this 3 in our set. And then this is a fully closed interval from -3 all the way to 2. And we're including -3 and 2 in our sets. Okay. So when we look at those inequalities, we can kind of see when we use parentheses and when we don't, when we use brackets. So this reiterates what I just said. A parentheses indicates that an endpoint is not included. When should we use brackets? So a bracket indicates that an endpoint is included. Okay. All right, so let's just get to an example of this, the way you may see it. Interval notation is a convenient way to describe intervals. When using interval notation, read the graph from left to right. So just like we do in a regular book, when we read from left to right, we read graphs in the same way. So this graph goes on forever in the left and on forever in the right. This is negative infinity all the way to positive infinity. With those arrows, it just means it's going to go forever. However, our interval is specifically noted in a particular part. So reading this graph from left to right, we start here at -3, and we're going to include -3 in our set. And it includes all the numbers from -3 until we get to a halting stop here at 2, and we are including 2 as well. Okay. So the textbook way of describing this is basically reading the graph from left to right. Minimum value, the lower bound, the smallest number in our set is -3. And the bracket indicates that we're going to include -3 in our set. Continue to read all the way to the right. We see the maximum value of the interval is 2. Again, it's bracket, so we include 2 in our set. What I do want to put in here is maybe like an example of when we would ever use this. Let's say we were describing the age of students in our class. And let's say the youngest person in our class was 18 and the oldest person in our class was 52. So on the number line, you know, obviously ages go forever, you know, maybe not forever. Maybe the oldest person in the world is 120, whatever. Anyways, because these are actual people in our class, we would include them in our set. So it would be bracket 18, bracket 52. Now, if I said there was a person who wasn't, let's say we just wanted to describe our number line as like 17 to 53. Then we'd say the people are aged between 17 and 53. So we wouldn't include 17 and we wouldn't include 53. So those would be soft parentheses. Okay. So that's just an example of an application of when interval notation could actually make sense for you and something that you do in your daily life. Okay. Express the interval notation. So here we have a half open interval or half closed interval, however you want to look at it. We have this open parentheses here, and I shouldn't have made, let me just keep going with the blue. Open parentheses here on -1. So when we write this, we say -1. Remember, we're reading from left to right. So we start the leftmost point, the smallest, the minimum value, and we say it goes up to 3 inclusive. So from -1 to 3, -1 not included, 3 included. And we know that based on the brackets and the parentheses that were given to us. But let's read the textbook method. Reading the graph from left to right, first mark is at -1. The parentheses indicates that the endpoint -1 is not included. Continuing to read the graph from left to right, the next marking is at 3. That's our maximum value, and the bracket indicates that the 3 is indeed included. So when we do this one, I want you to try this one on your own. Pause the video. See if you can write this as an interval notation. Okay, now that you've given that a try, from left to right, we have the first marking at -2. And it's an open parenthesis, so that means that it is not included. And it goes up to +2, again with an open parenthesis, meaning that 2 is not included in our set. So that is exactly what we just said. The first marking is a -2. The parentheses indicates that the endpoint -2 is not included. Continuing to read from left to right, the next marking is at 2, and the parentheses indicates that 2 is not included. And that's interval notation. Now, we do need to notate that when you see something like this, -2, +2, your mind may be thinking X, Y coordinate points. But in interval notation, that is not what we mean. We are looking at this as a set of numbers between -2 and +2. So we're talking about -1, 1. We're talking about 0. We're talking about 1.99999, but we just can't include 2. So we have to think about the context to determine if it's a point, -2, 2, or if it's the interval X values between -2 and +2. So when I say you must consider the context, we're going to have to see what type of problem we're doing and like make that make sense. If we're talking about a point, then we know we're talking about X, Y coordinate. If we're not talking about a point and we're talking about an interval, we know we're talking about numbers between -2 and 2. Express the in interval notation. So earlier I told you, earlier I mentioned that a number line is continuous. And so from the left, it's -infinity, meaning the smallest number you will ever reach, which is in actuality not really a number, but -infinity all the way to +infinity, the biggest number that you will ever ever reach. So to infinity and beyond, you know, Buzz Lightyear kind of thing. So we have the negative infinity all the way to positive infinity from left to right. And the boundaries are the markings that we have. Sometimes there's no upper bound, sometimes there's no lower bound. And so in this particular example, we'll see that there is no upper bound. And so reading the graph from left to right, we see that the first point or the first marking on our graph is at -3. And -3 is marked by parentheses, meaning it's not included in our set. So maybe -2.999999, but not -3. Okay. And so we keep going. So it's not included. And then we'll see the arrow to the right means that the interval does not have an upper bound. So there is no maximum value. The symbol infinity is used to indicate this. Let me not write on top of that. So we have -3 to infinity. And my question to you is, what do you think? Are we going to put a parentheses or are we going to put a hard bracket on infinity? Well, you can see the answer here. We would definitely put the parentheses because infinity is a construct that you actually can never reach. So we can't actually touch infinity. Therefore, it would not be included in our set, but that's the direction in which we're headed. We're headed towards infinity, positive infinity. So we put that like that. Okay. So there's always a parentheses next to infinity because it does not represent a real number and should not be included in the interval. So in this case, from left to right again, we're going to say, hey, this left arrow, so there is no lower bound in this case, indicates negative infinity. And then we're going to be going up until 1. And 1 in this case is included because we have a bracket. So this bracket indicates an endpoint of 1. So negative infinity to 1 is what that indicates. You'll have plenty of examples that you can practice on your homework, but right now we're just kind of giving you the gist of all the different ways you may see it. Expressed in interval notation. So again, it's negative infinity to -2 in that point because we're going from left to right. But there's a double interval here. So we also have and. This little symbol right here is a way to write and in math. Okay. We have 1 all the way to positive infinity. Don't include 1, don't include positive infinity. We only included the 2 because of this bracket here. Okay. So let's slow this down and see what the textbook has to say. We clearly read the graph from left to right. The gap indicates that there are 2 intervals here that we're looking at. So that was this first interval, and then there's a second interval that we're going to be able to write. The arrows to the left indicate that there's no minimum value, so we use negative infinity to indicate this. And then the bracket of -2 says, hey, we're going to include -2. That's that. The parentheses on the 1 says it's not included, but the arrow says, hey, there's no maximum value, so use positive infinity to indicate that. And the union symbol is the way to join 2 sets. You may also use a comma if you just want to write it, like write the 2 and list them. But the union, the U, just means and in math. Okay. All right, I need to spice this up because I don't want you to be getting bored while you're watching this video. So let me use a little inflection in my voice. I see that there are 2 different intervals here. There is a gap. That gap is basically telling me that 1, the number 1, is not included in my set. So there are multiple ways for you to write this. And we're going to talk about a couple of different ways for you to write it. So the first thing, just reading from left to right in the way we know how to do, we can see that this is a negative infinity up until 1. And this one says 1 to positive infinity. And clearly the 1 has soft parentheses on either side. So that's one way to say this in interval notation. Another way for you to say this is all real numbers except 1. because 1 is the only number on this set that's not included. But reading from left to right, we see that there are 2 intervals and 1 is not in either of those intervals. So we'll write it as such and put the union symbol. Okay. Express this interval. Wow. It's just forever. So again, don't let it scare you. We're reading from left to right. Left meaning negative infinity. There's no lower bound. And there's no number that had a marking, so we're going all the way to positive infinity. Again, there's no upper bound. So the way we would write this is indeed negative infinity to positive infinity. Done, done. Yes. That's how you say all real numbers. Okay. All right, so we are done with that first idea of just building, like using interval notation. And so now we're going to talk about how set builder notation can be used to represent um, intervals, and then how we can write interval notation from set builder notation. So set builder notation is something that it's like each symbol represents a word, and then all these words together make a sentence. And so it's kind of translating between math and English, if you will. So like, let's say this: curly bracket, X, line, X, not equal 1, curly bracket. So curly brackets mean the set. Okay. X, this first X says the set of numbers X, like it just represents a whole bunch of numbers. This line right here is such that I'm about to describe the set. So we have a set of numbers X such that this is true about them. And then this is the statement. The statement says X cannot equal 1. So we have a set of numbers, all these numbers, but 1 cannot be in that set. That's basically what that means. Okay. Okay. So it says express the following in interval notation. So they'll give it to us as set builder, and then we'll have to interpret what that means in terms of an interval. So this says the set of numbers X such that X is greater than 1 but less than 5. So X is greater than 1 but less than 5. Notice I use parentheses. And the reason for my parentheses is because this is greater than and not greater than or equal to. This is less than 5. So it's greater than 1 and less than 5. Okay. The next one says a set of numbers X such that X is not equal to. So all real numbers except for 2. So we got from negative infinity all the way to 2, not including 2. And from 2 all the way to positive infinity. And so we just are basically saying don't include this 2. But everything else can be included. All right, this set says the set of numbers X such that X is not 4 and X is not 6. So we're going to go from negative infinity. We're going to take out negative 4. And we have to take out positive 6. So we're going to go from negative 4 to 6. And then go from 6 to infinity. So in essence, we had to remove the 4 and remove the 6 by putting soft parentheses around the negative 4 and soft parentheses around the 6. So I'm feeling that somebody didn't really get that. So I'm going to slow this down and I'm going to explain it one more time. Okay. Using a number line, we're saying, hey, don't include 4. -4, I'm sorry. Don't include 6. But include all the rest of the numbers. And so in this interval, we have -infinity all the way to -4. In this interval, we have -4 to 6. And in this interval, we have 6 to positive infinity. And that's how you exclude. Sometimes it's really important to go back to the graph because the graph helps those visual learners. Okay. All right, so now we're evaluating functions. So this is really the nitty-gritty of when we get to what the work is going to actually look like on the homework. Everything we've done thus far has been really just building up your knowledge of what you're going to see and what it actually means. Okay, so let's put some application to it. Although thunder is caused by lightning, we sometimes see a flash of lightning before we hear thunder. The further away lightning is, the greater the time lapse between seeing a flash of lightning and hearing thunder. So the time lapse between seeing lightning and hearing thunder in seconds is right here and given as x. The appropriate distance y in miles between the person and the bolt of lightning. So you may hear, this is the time lapse between seeing the lightning and hearing the thunder. And then this is how far the distance between the person and the bolt of lightning. Because each x determines exactly one y, we say that this table defines a function. So 5 goes to 1 mile, 10 is 2 miles, 15 seconds is 3 miles. You can kind of see a pattern here. Looks like times 5 every time to me. Or divided by 5, I'm sorry. Okay. We can say that y is a function of x. In this case, the distance between the observer and the lightning bolt is a function of time. Y is a function of x. So using the same table, we can express this data as a relation by listing out the different ordered pairs. So let's do that. We have 5 compares to, 5 corresponds to 1, 10 corresponds to 2, 15 corresponds to 3, 20 corresponds to 4, and 25 corresponds to 5. So these are just XY coordinate points, and we wrote them as XY coordinate points. Okay. And so that is how you list out ordered pairs. Okay, but now we're going to kind of give these some names. The domain of a set is all of the x values, okay, or the inputs of a function, the x values. So in this case, the x values are 5, 10, 15, 20, 25. And so we're going to list those as the domain, 5, 10, 15, 20, 25. Whereas the range is the list of all of the outputs or the y values. So these are the x values. Don't know why I said that, okay? And these are the y values. Range is y, x is domain. And so we're going to list the range being all of these, 1, 2, 3, 4, and 5. Uh-oh, didn't want to go too fast. Okay, so basically we have functions, and we know that the function has an input and an output. The input is x, the output is y. So Dixie and Roy, girl and boy, whatever, however you want to look at it. Dixie is domain. I stands for input. And then these are the x values. So that helps you to remember that domain and input are x values. Range and output are y values. So range, output, y values. So for example, if we have the point 10, 2, then in function notation, we say f of x is y. So we would say f of 10 equals 2. So inside of the function is where we put our x, and that equals y. Okay. So that's really important for you to know. F of x equals y. The thing inside of the function is the x. The thing that comes out of the function is the y. Hence, input for inside and output for what comes out. Okay, so we read this as f of 10 equals 2. F of x equals y. F of x equals y. That's how you read that line. Okay, so example 11 says complete the following. We have this table and it says determine f of 5. So that means the x value is 5, because remember, the number inside represents the x, or the domain, the input. And so f of 5, what was the output? The y value, 1. F of 5, I'll write this right here, f of 5 equals 1. F of input equals output, therefore f of 5 equals 1. Okay. All right, we have B. If negative 4, 7 lies on this graph, then how could we write it as a function? So g of which one of these values is your x value? The 4 and the 7. Negative 4 is x, 7 is y. So f of x, which in this case is negative 4, equals output y, 7. Okay. So this is just called function notation. Again, this is just what you're going to be dealing with all semester. And so we want to give you some foundation understanding of how this works. Complete the following for the graph, for the function. So we're going to be finding values f of 1 and f of a plus 1. So f of 1 means that x is equal to 1. So if our function f of x equals 4 over 2 minus x, we'll take this x, replace it with the 1, and then that means this x also gets replaced with 1. So notice that we're putting 1 in the place where x was. And then we do the math. 4 divided by 2 minus 1 is 1. 4 divided by 1 is 4. If f of a plus 1, that means that a plus 1 is going to be substituted in for all of our x's. So we have f of a plus 1. That means inside of this function, we're going to put a plus 1 where x was. And then we see this whole sentence, 4 divided by 2 minus a minus 1. So we can already do the 2 minus 1 piece, and that leaves us with 1. So we'd have 1 minus a. So 2 minus 1 minus a. That's called the commutative property, so you can move numbers around. And 2 minus 1 is just 1, so we end up with 1 minus a. Okay. All right, so all of that, again, is just kind of building you up to know where we're going. And just to do a status check, we're on example 12, and there are 19 examples in 1.3. So you are almost there. Stop and pause the video if you need to, come back to it. But I definitely want you to be prepared to discuss this in class. So let's keep going. All right, the next one, 12b. Complete the following for the function f of x equals 4 over 2 minus x. Same thing we just were doing, but it says find the domain of f. Use interval notation. Well, the domain, again, the domain is all of the x values that make up the set of values for a particular function. But in this case, we don't really have any. We just say it's x. Okay. But be sure to check the following. These are two rules in math that you are going to have to memorize and know and understand for this entire course. And it's going to come back and back and back and back. So please take a moment. Y'all see my little star here. This is extremely important. Okay. The denominator can never be 0. So in an expression, if you have a fraction, this one could never actually equal 0. So we could put any number into this function and it'd be a part of the domain, except numbers that would make the denominator 0. The denominator can never be 0. The denominator could never be 0. So any number that would in turn make the denominator 0 is not a part of the domain. Okay? Also, if we have any square roots, then the square root could not, the number expression under the square root could never be negative, because we don't take the square root of negative numbers in the real number system. So that's important. Okay, we're not going to have negative numbers under a radical or under a square root symbol, and we're not going to have anything that is divided by 0. So in this case, we're trying to say basically this expression in the denominator cannot be 0. And we have to find out which number x would make it 0, because that would be our number that cannot be a part of our domain. Okay. And so basically what we're going to do is we're going to solve for x. Okay. So you can see what the textbook did, but I'm basically going to do it again and just take you step by step. Add x to both sides because we don't want a negative x. And we say 2 cannot equal x. In other words, x cannot equal 2. If x wasn't going to equal 2, then we would have a 0, because you could see that 2 minus 2 is indeed 0. So x can never be 2 as a part of our domain. So the domain is all real numbers except for 2. And if we look at that on the number line, like we were earlier, all real numbers except for 2. How do we write that in interval notation? Well, we say from negative infinity to 2, and from 2 to positive infinity. Just like that. The set builder notation is a set of x such that x is not equal to. That's it. So on the test, it will ask you for particularly, what's the interval notation, or what is the set builder notation? And so knowing how to write both of those is really important. Okay. Again, there's a star here, so pay close attention. Use the graph to complete the following. Estimate the domain and range. Use interval notation. So we just showed you how to do it if you're giving the function like as a in numerical form. So you may have like an actual function, you have to solve something and you have to see what, like if my denominator can't be 0, or there's a radical and it can be negative, whatever. Sometimes we'll give it to you as a graph and you can visually see it. So the x-axis represents our domain. So you can see that this graph starts at 2 and there are values forevermore. So I would say my domain is from 2 to infinity, including 2. And I knew to include 2 because there's a point at 2 at which it is defined. Okay, so let us look from left to right for all the possible x values. The domain is positive 2 all the way to infinity, because we have a function that covers this domain. Okay. So you could also, because they gave us the formula, you could also say, hey, this stuff underneath the radical, the square root symbol, cannot be negative. So we say x minus 2 must be greater than 0. That's how you say it cannot be negative, because it has to be bigger than 0. Add 2 to both sides. X has to be greater than or equal to 2. So starting at 2 and all the numbers bigger than it. That's that. Okay. Now, for the range, we're going to be looking from the bottom of the function all the way to the top of the function. So the function, so we're going to look at the y-axis. There's nothing down here, right? The lowest we see is right here on 0. So our range starts at 0. And there's something at 1, there's something at 2, there's something potentially at 3 because this arrow is going forever. So it's going to continue to go forever. So our range here starts at 0 and it just goes up forever towards infinity. And we write that as 0 to infinity. If you're having difficulty finding the domain and range from an equation, try sketching the graph and using the graph instead. So now you know you have two different ways to look at this. Either use this equation or use the graph, and the graph will help you. Getting a TI-84 or 83 calculator is going to be really helpful for you to be able to see the graph and visualize where your domain is and where your range is. So now it says evaluate the graph of f of 0. So f of 0 says x is 0. So if x is 0, there is no function value. So I would say it's not defined because x is not even a part of our domain. Yes, it's undefined. Again, you can stop and pause this video and let it go at your own pace. And hopefully, it'll make more sense to you. Number 14, star, asterisk, asterisk. Y'all, this is important. Estimate the domain and range from the graph. Use interval notation. So in here, we're going to, again, be looking from left to right on our domain. So if you were to flatten your graph out, and that's how I have to imagine it, it would lie on this x-axis, and you would see that there are arrows on both ends. So arrows on both ends means we're going to be going from negative infinity all the way to positive infinity with no stops. So our domain is indeed negative infinity to positive infinity. Okay. Notice that there isn't a denominator or a square root in this equation. Therefore, we don't have any restrictions on the domain. Like, let me say that again. This is our function. There are no fractions. There are no square roots. So we don't have any restrictions. Those are the only two things we have to really look out for when we're looking for restrictions in the domain. Okay. Now, for the range, we're looking from bottom to top. So the lowest value here on the y-axis that actually has a value is -1. Okay. So -1 is defined right here. And then when we move upward, like there's nothing down here. There's nothing down here. So our lowest value for our range is -1. But then our graph is defined everywhere else from then on, going up. So our y-axis started at -1 and went up to infinity. So that's going to be how we represent range. Okay. All right, so that's really important, especially for your quiz that's coming up and for the exam that you will have. Can you identify the domain and range given a graph, given an equation? Can you do that? All right, use the formula this time to evaluate g of -1 and g of 1. So again, g of -1 means that x is -1. So we plug in -1 for all of the x's in the equation. So g of -1 equals -1 squared minus 2 times -1. -1 squared is +1. Negative 2 times negative 1 is positive 2. 1 plus 2 is 3. So that's our output. Input of g of 1 means that x is 1. So we're going to plug in 1 everywhere. 1 squared minus 2 times 1. So we have 1 minus 2 because negative 2 times 1 is negative 2. And so 1 minus 2 is negative 1. So that is our output on that. Now we're going to use the graph to verify this. So you find the point where x is negative 1. So when we find g of negative 1, x is negative 1 right here. And you go find where the y value is. Boom, it's at 3. And that would make sense. Right here. Okay. Then for g of 1, you go and look at the 1 on the x-axis and you say go down. It's right here, negative 1. And you can see that those are defined in those ways. All right, so evaluating function diagrams. Complete the following. So you can evaluate f of 15. So f of 15, remember, 15 is the x, so we look at this first bubble. The input of 15 goes to the number 3. So f of 15 is 3. Given the domain and range, so recall that the domain is a set of all the inputs and range is the set of outputs. So this is the inputs, the blue. This is a set of outputs, the red. So the domain here is 5, 10, 15, and 20, whereas the range is 1, 2, 3. Okay. Representing functions, symbolic, numerical, graphical, and verbal. So there's different ways that we'll see a function. Symbolic means we gave you the equation. Numerical means that we gave you the table. A graph, of course, graphical is graph. And then verbal is where we actually describe it. So f squared, f squares input x and then adds 1 to produce an output. So x squared plus 1 is f of x. That makes sense. All right, so right now we're just kind of defining some things because we're going to be able to check and see if we have a function. A function is really just something that allows us to predict what's going to happen. And a function can be written in different ways, just like we showed you, numerical, graphical, verbal, symbolic. But it's basically where each input matches to only one output. So if I tell you to push a button on a vending machine, that vending machine should give you the same thing out every time because that's the only thing that that button is going to indicate. So if you push the button, the first button on the machine, it should always give you Sprite. You should know what's going to come out when you push that first button, or if you push the second button, you should know what's going to come out. And so that's the definition of a function. But there's a test that we can do to see if a relation is actually a function. It's called the vertical line test. And so let's just see it. If you draw a vertical line on a relation and it only hits the relation one time, then that means it is a function. Okay. So every vertical line that can be visualized could intersect the graph at most once. Therefore, it's a function. Whereas B over here, if we draw a vertical line, it hit 1, 2, 3 times. If we hit it over here, it hit 1, 2, 3 times. So you see that this is hitting more than once. So therefore, it's not a function. Okay. So that's the vertical line test. And remember, when you see the stars and the asterisks, that means you'll see it again maybe on a quiz or a test. So make sure you pay attention there. Okay, so now we're going to identify functions just from looking at their values. So here we have 1, 2, 3 in our x values, and none of them are repeated. The y values can repeat all day. That's totally fine. But because we have 1 and it matches 2 maps, 3 maps, that is a function. Okay. Whereas here we have 2 mapping to 1 and then also 2 mapping to 2. That is not a function because 2 maps to 2 different things. And if you see this visually, 2 maps to 2 different things. So a vertical line would touch both of those. So that would be not a function. Okay. H of x equals 1 minus x is a function. So yes, this is a function. And what we do is we'd actually graph it in our calculators and do the vertical line test. But 1 minus x is actually a line. So it would lines don't curve and turn and stuff. So therefore it is a function. Whereas this one, x squared plus y squared equals 4, it's actually a circle. So if we graph that in the calculator, we'd see that it's a circle. And it's not a function. It's a circle because a circle does not pass the vertical line test. It's going to touch twice on most vertical lines. All right, 2 more and we are done with this lesson. So write a symbolic formula for the function g that calculates the given quantity. Then evaluate g of 10 and interpret the results. So the number of minutes in X amount of days. So first off, we need to find out what our X is and what our Y is, or what our input is and what our output is. The number of minutes in X days. So if we know the number of days, then we can find out the number of minutes. So we have to put in the number of days and come out with the number of minutes. So I'm thinking input is days, output is minutes. Okay. So we need to find out how many minutes are in one day. Well, that's easy enough, right? So let's start with what we let's start with what we do know. We know how many minutes there are in an hour. So there are 60 minutes in an hour, and there are 24 hours in a day. So therefore, there are 1,440 minutes in a day. Now we can look for a pattern. Well, if there's 2 days, we just multiply this number by 2. If there are 3 days, we multiply by 3. 4 days, we take that number and multiply by 4. So if there's X amount of days, we just take that 1440 and multiply by that number of days, which we represent with an X. So our function g of x equals 1440 x. So g of 10 would equal 1440 times 10 because that's 10 days. How many minutes are in 10 days? 14,400 minutes are in 10 days. And there we go with our interpretation. All right, number 19, asterisk, star, star. Let's do it. The graph shows the amount A of water in a small swimming pool after X amount of hours. So when you started off at 0 time, there was no water in the pool. So what is the initial amount of water? None. The pool was empty. And then if we read this, it's like, okay, we're filling up the tank. The pool. And it looks like it took 4 hours and we stopped at 500 gallons of water. What a waste. Just kidding. It's hot. I would love to be in that water right now. 4 gallons. I'm sorry, 4 hours. And then we had 500 gallons. So evaluate A of 4. So right here we would put A of 4 equals 500. Let's interpret it. After 4 hours, the pool contained 500 gallons. It says estimate the domain and explain what this means. So the domain is the number, like the amount of time basically that we're looking at from 0 to 12. So at first, initially, there was no water. We filled it up to 4 for 4 hours. We swam for 4 hours, and then we drained the pool for another 4 hours. So from 0 to 12 is our domain. It means over a 12-hour period, the amount of water in the pool was recorded. The range, however, is going to be these Y values from 0 gallons to 500 gallons. So the minimum amount of pool water was 0 gallons. The maximum was 500 gallons. So from 0 to 500 is what we're looking at. And this means the amount of water in the pool over a 12-hour period was from 0 gallons to 500 gallons. So y'all made it. That is the end of our first flipped video for class, section 1.3. Thank you for watching.